Bismillahirrahmanirrahim. Welcome back to Mathematical Methods of Physics, lecture number 17. Before I start lecture number 17, let's review what we have studied so far in last lecture and so far in the current topic, which we have been discussing for past 3-4 lectures. Method of separation of variables is the topic that we have been studying in from last 3 lecture, I guess. Today is the 4th one on this topic, or 5th one. We have implemented this technique for parabolic equations, in particular heat equation, to hyperbolic equations, in particular wave equations, and to elliptic equations, in particular to Laplace equations. Then in the last lecture, specifically, we moved on to implement this separation of variable technique to equations with more than 2 independent variables. So we solved it for 2 spatial and 1 time variables, the wave equation. We took the rectangular membrane and studied the vibration of a rectangular membrane. So it gives me the 2-dimensional wave equation, 2 variables, 2 spatial variables x and y, and 1 time variable t. And then we move on to study the same wave equation in a circular membrane. So we converted our equation from x, y to r theta, and we solved the equation in r, theta, and t. Alright, and we have seen that for equations in circular membrane, we come up with a new equation called the Bessel equations. We used the solution directly, we didn't solve it, but I will be solving these 2 Bessel equations later on in our later lectures. So that will give you more idea about the Bessel equations. Today we are moving on to a very important problem. Basically, this is called a Sturm-Liouville problem, Sturm-Liouville system, or Sturm-Liouville problem. In short, we can call it SL problem. S for Sturm, L for Liouville. 2 mathematicians, they created this problem, so named after them. Properties of the regular Sturm-Liouville problem. So we will be doing properties of this SL problem. If you recall, you will be seeing that in last lecture we actually have been solving this system, SL system. We have solved SL system for almost all the equations where we implemented method of separation of variables. Alright, just to recall that x double prime plus lambda x equal to 0 subject to homogeneous boundary conditions was an example of SL eigenvalue problem. Alright, so we will be writing the general form of SL problem and we will be discussing the properties of that. So what is SL system? The second order differential homogeneous equation, which is d by dx or x u prime plus qx plus lambda px u is equal to 0. It's a second order differential equation with parameter lambda in it. You see, lambda is a parameter. Px, qx, and rx are continuous functions on the interval a to b. Alright. It's a Sturm-Liouville equation. U is unknown variable here. It's second order because you see the derivative of the derivative. D by dx of u prime is the second derivative. In the operator notation, the above equation may be written as, if you write the operator notation, you can write it as Lu plus lambda pu is equal to 0. So I separated this lambda px u is equal to 0. I separated this, and the first 2 terms, d by dx of rx u prime plus qx, this is called the operator L here. We define this as an operator L. Lu, so L is d by dx of rx plus qx. If you apply L on u, you will get d by dx of rx plus qx implemented on u. Here lambda is of course the parameter. Then we have a regular SL equation. This is a general SL equation. Then we have a regular. What is the regular? What is regularity in this equation? The blue equation, this colored equation, blue equation, is said to be regular SL equation if qx or x does not vanish at any point of the interval. Alright, so it means if qx and rx, they will never be 0 in this throughout this interval. It means that there is no point x between a and b where qx or r of x, they become 0. All right, then it is called a regular SL problem. The colored equation, blue equation, which is of course given here, SL problem, is said to be singular if it is not regular. If one of them, if rx or qx becomes 0 somewhere, all right, then this will be a singular SL equation. Periodic SL equation, if this equation will be called a periodic if rx, qx and px are periodic functions with fundamental period b minus a. If any one of these, if all these functions px, qx and rx, if they are periodic functions, then we call this equation a periodic SL equation. All right, so we have three properties right there: regular SL problem, singular SL problem, and periodic SL problem. All right, we will be studying regular SL problem in quite detail because this is a better behaved system. The regular Sturm-Liouville equation together with the linear homogeneous boundary condition is called a regular SL system, because now it's a system, it's a boundary value problem now, equation with respect to the boundary conditions, and boundary conditions are homogeneous boundary conditions here. All right, if your SL equation is periodic, then your boundary conditions will be like this. The periodic SL equation together with the periodic boundary condition is called a periodic SL system. Boundary conditions are also periodic, where u of a is equal to u of b, u prime of a is equal to u prime of b. We took b minus a as a period, so ua and ua plus p will give you ub. So examples of the regular SL system: u double prime plus lambda u is equal to 0. Conditions are boundary conditions are homogeneous, that's fine. If you see, your r of x is 1 here, because if rx is 1, then you will get u double prime here directly, because d by dx of u prime is u double prime, and this is what you are having here, plus lambda u. It means qx is 0 and px is 1, because there is no term without lambda, so qx is 0 and px is 1. So qx is 0, rx is 1, so rx is never 0 in this interval. All right, so it means this is a regular SL system. Here again qx is 0, but rx is 1 minus x square. Your equation is your conditions are 1 by 2 and 3 by 2. So from 1 by 2 to 3 by 2, this rx is never 0. Rx is 1 minus x square, and it is only 0 when x is equal to 1. All right, so let's see some examples of the regular Sturm-Liouville systems. Regular Sturm-Liouville system, this is the regular one because rx is 1, never vanishes between the interval. Regular SL system, this is the example of regular SL system. u1 by 2 0 and u3 by 2 0. Your interval is from 1 by 2 to 3 by 2, and this should be 1 plus x square here, or interval should be from negative 1 by 2 to 1 by 2. At 1, if it is vanishing, it's not a regular system. Singular SL system, here clearly again 1 is in the interval 1 minus u square, just by changing the intervals. This should be from negative 1 by 2 to 1 by 2, and this is from negative 1 by 2 to 3 by 2. Just to make the condition to 3 by 2, 1 is included in the interval, and this is vanishing at 1. Here 1 was not included in the interval, so it is regular. This is 1 by 2. It's a mistake. Negative 1 by 2 and 1 by 2. Periodic SL system. Here you see the function given here is a periodic function. All right. 1 plus 16k cos 2x cosine is a periodic function, and here the boundary conditions are also periodic. That's why this is called a periodic SL system. All right. So these are examples of regular SL system, singular SL system, and periodic SL system. Remark, clearly u is equal to 0 is always a solution of the problem. You see, this is always the solution of the problem, because when u is 0, it's a homogeneous equation. So homogeneous equation always have 0 as a solution. So homogeneous equation always have 0 as a solution, subject to the homogeneous boundary condition. So of course u is equal to 0 will be the solution. But it is of no practical use. If you want to find just 0 solution, then what you have to do with it? So usually whenever we solve the SL system, we look for the non-zero solutions, non-trivial solutions. What we want to find is the solutions of the above equation satisfying the boundary condition without being identically equal to 0. We call such a solution if it exists an eigenfunction, and the number lambda for which an eigenfunction exists is called the eigenvalue of the problem. We have been doing this before as well in method of separation of variables. We came up with different boundary value problems where lambda was a parameter inside, and we defined the eigenvalues, eigenfunctions there as well, that values of lambda for which this system has a non-trivial solution is called the eigenvalue, and those non-trivial solutions are called the eigenfunctions of the system. If you look at here, this is u double prime plus lambda u is equal to 0. It is the same equation which we have been solving in different PDEs when we use separation of variables with boundary conditions, something like this, right? So basically we have already solved a special case of Sturm-Liouville eigenvalue problem, all right, and not just once, many times we have solved it, all right. So basically whenever we cope with the SL system, we look for the non-trivial solutions and we look for the eigenvalues that gives you the non-trivial solutions. So basically we look for eigenvalues and eigenfunctions of the SL problem. That's why sometimes it is called Sturm-Liouville eigenvalue problem, all right. So let's see some properties of the Sturm-Liouville eigenvalue problem. What are the properties? First of all, the first property is that these are the properties of regular SL system. Regular, all right. There exists an infinite number of real eigenvalues that can be arranged in increasing order, lambda 1 less than lambda 2 less than lambda 3 and so on up to infinity. So if you recall, in our previous lectures, our lambdas were usually n pi by L square or n pi square. So for n is equal to 0, it's 0. For n is equal to 1, it's pi square, then 2 pi square, then 3 pi square. So they can be arranged in increasing order, all right, and there are infinite many values. So whenever we have a regular SL problem, we will have infinite many real eigenvalues with this arrangement. For each eigenvalue, there is only one eigenfunction. And again, if you recall our eigenfunctions, usually we have cosine nx or sine nx. So we have unique eigenfunctions for one eigenvalue, all right. Eigenfunctions corresponding to the different eigenvalues are linearly independent. Of course, cosine 1x is linearly independent of cosine 2x, then cosine 3x, and cosine 4x. So these are always linearly independent functions. The set of eigenfunctions corresponding to the set of eigenvalues is orthogonal with respect to the weight function rho x on the interval AB. So our rho x is important here, which comes with the lambda. If it is just lambda u, then weight function is 1. If that term is lambda rho x u is equal to 0, then rho x is the weight function. Then your orthogonality will be with respect to the weight function. Sin x, cosine x can be orthogonal with respect to weight function 1. But if your equation has lambda rho x u is equal to 0, then your eigenfunctions u1x, u2x times rho x dx will give you 0. If you ignore rho x from there, integral may not be equal to 0 and they may not be orthogonal to each other, all right. So these are the 4 basic properties of the regular SL problem. Let's move on to some propositions now. Proposition 1 is any two eigenfunctions umx and unx corresponding to distinct eigenvalues lambda m and lambda n of a regular SL system subject to the homogeneous boundary conditions given by this are orthogonal with respect to the weight function rho x. That is um and un, the integration of the product of and un with this rho x will give you 0. All right. So proof of a proposition 1. All right. The given regular SL system is d by dx of Rx du by dx plus Qx u plus lambda rho x u is equal to 0, subject to the boundary conditions alpha u a, alpha 1 u a, beta 1 u prime of a is equal to 0, alpha 2 u b plus beta 2 u prime of b is equal to 0. Now since um and un x are eigen functions, corresponding to eigenvalues lambda m, lambda n respectively, right? We have, it means your un satisfies this equation. D, if I replace u by um here and lambda by lambda n here, it will give you 0. Similarly, u by un and lambda by lambda n also gives you 0 because they are the solutions and they will also satisfy the boundary conditions as well. So this implies that d by dx of Rx dum by dx plus Qx um plus lambda m rho um is equal to 0. All right. And d by dx of Rx dun by dx plus Qx un plus lambda n rho un is equal to 0. Right. Subject to, also we must have alpha 1. So alpha 1 um at a plus beta 1 u prime m at a is equal to 0, and similarly alpha 2 um at b plus beta 1 um prime at b is equal to 0, and un also satisfies the boundary condition. So un at a plus beta 1 un prime at a is equal to 0, alpha 2 un at b plus beta 2 un prime at b is equal to 0. So these all are, will be there because and un are the solutions of the system. So let's call it 1 and let's call it 2. If I multiply this by un and this by um, so if we multiply 1 by un and 2 by um and then subtract, then subtracting we get, you see, if this multiplied by un and this by m, this multiplied by un and this by m, they will be cancelled. This multiplied by un and this by m. All right, what you will get is you will get un d by dx of Rx dum by dx minus um d by dx of Rx and dun by dx. Right, this is from the first term. These will be cancelled out because qx un qx un they will be cancelled out. Here you will have lambda un as common, so you will get lambda m minus lambda n. So plus lambda m minus lambda n rho un equal to 0. Here you see derivative of this thing un as it is minus derivative of this as it is. So it's kind of product rule. You can write this d by dx of un or prime minus or un prime. This is what you will get, equal to, I am sending this on the right hand side, lambda n minus lambda m rho un. Here you can simplify and see this is true. If you take un as it is, derivative of or prime, all right, and then or prime as it is, derivative of un, that will be cancelled with or un prime as it is, derivative of they will cancel, and at the end you will be left with as it is, the derivative of or un prime. That's why if you use product rule on this two and product rule on these two functions, product rule on these two functions, the first from here and the last from here will retain, the between two will cancel each other. All right, that's why there are no 4 terms. There should be 4 terms. 2 of them will be cancelled and 2 left will be exactly these 2. All right, you can clearly verify this thing. Now see, derivative is up front here, you can integrate. If you integrate from a to b, you obtain un or prime minus or un prime from a to b, because derivative and integral, they will be cancelled of course, equal to lambda n minus lambda n is constant, so integral will go to from a to b rho x un x dx, and we need to prove this thing equal to 0, right? We need to show this thing. So I have to show that this left hand side is 0. So let's simplify the left hand side. R and R is common here. So I can take the value at b first. So this is, so let me write the left hand side on the right hand, on the left hand side, because this is what we need, so I can keep it on the left. Rho x x un x dx. All right, equal to R at b, and this is common, so I'm writing it outside, and you have un prime. So un at b, prime at b minus un prime, minus at b and un prime at b. This is first thing, minus r at a, all the things at a now. So un prime at a minus un prime at a. This is what you are getting. All right. Now from boundary conditions, we have prime of b is equal to minus, if you go back here, you see prime of b is minus alpha 2 by beta 1 umb. Minus alpha 2 by beta 1 umb. All right. Similarly, prime of a is minus alpha 1 by beta 1 UMA. Un prime of b is minus alpha 2 by beta 2. So this is also beta 2. This is beta 2. Minus alpha 2 by beta 2 un of b, and un prime of a is equal to minus alpha 1 by beta 1 un of a. So it means I can replace all these derivatives by these without derivative terms, but there will be a factor of minus alpha 2 by beta 2. So this above equation becomes, so therefore the above equation becomes lambda n minus lambda n on the left hand side, they will remain there, dx equal to, or at b, inside we have u and b, so u and b remain there, un prime of b, um prime of b is this one, alpha 2 by beta 2 umb, umb and minus alpha 2 by beta 2, and minus will become plus, and this is unb is alpha 2 by beta 2 unb. All right, so again this is minus alpha 2 by beta 2, you will get umb was already there and un prime becomes umb, and then minus r of a, you have r of a una, so una as it is, prime of a is alpha 1 by beta 1 uma, so minus sign uma with alpha 1 by beta 1, and then minus uma right there, and un prime of a is minus alpha 1 by beta 1 una, so plus una alpha 1 by beta 1. So this is what you got. Now you see they are clearly 0. Alpha 1 by beta 1, una, and minus sign. So this is gone, this is gone. So right hand side is rb times 0 minus ra times 0. This is equal to 0. Since lambda n is not equal to lambda n, because these are two distinct eigenvalues, so this factor is also not equal to 0. This implies that un minus is not equal to 0. If this is not equal to 0, then this has to be equal to 0 because the product is 0. So this implies that a to be umx unx rho x dx is equal to 0, and this implies that umx and unx are orthogonal functions with respect to the weight function rho x. All right, so this is the proof of the, so this is proved, right? This is what we had to prove, that the eigenfunctions corresponding to the distinct eigenvalues are orthogonal with respect to weight function rho x. So we proved this thing. All right, next is the proposition 2. If rho x preserves the same sign in the interval, then the regular SL problem subject to the given boundary conditions must have real eigenvalues. See, we have no guarantee that regular SL problem will have real solutions, but the condition is that if rho x preserves the same sign, preserves means if it is negative, it remains negative throughout the interval. If it is positive, it remains positive throughout the interval. Then your SL, regular SL system will have only real eigenvalues. There won't be any complex eigenvalues. All right, this is the proposition 2. So let's prove this proposition as well. Okay, so we will prove this proposition by taking the contradiction. Let's assume on the contrary that lambda can be complex. All right. So suppose that on the contrary that lambda is complex, or I can say that lambda SL problem can have complex eigenvalues, and then we will prove the contradiction. It means what we assumed at the beginning, lambda is equal to complex, is not possible. So that is, let's say lambda is equal to alpha plus iota beta. Let's say this is a complex number, and let you, if eigenvalue is complex, then we can expect the eigenfunction to be a complex function as well. Then let ux is equal to phi of x plus iota psi of x be the eigenfunction corresponding to lambda alpha plus iota beta. All right, so let these two things. Then we have, if this is the case, then our SL problem must, then this ux must satisfy the SL problem. Then Rx and d by dx of u is phi plus iota psi, plus qx u, and u is again phi plus iota psi, plus lambda rho x u, and u is again phi plus iota psi is equal to 0. And here I can separate the real and imaginary part, separating real and imaginary parts. We obtain, if I take just phi, then this will be d by dx of Rx d phi by dx and qx phi and lambda phi. Plus lambda rho x phi, and then with iota you will have d by dx of Rx d psi by dx plus qx psi, and this lambda is also alpha plus iota beta. So you have alpha rho x psi and minus beta rho x psi. These both are without alpha. So you got alpha rho x psi minus beta rho x psi without, so and with iota you have, beta rho x alpha rho x psi. So you got alpha rho x psi and minus beta rho x phi. So this is equal to 0. So if this whole thing is equal to 0, it means the real and complex parts should be equal to 0. Otherwise, complex function can never be equal to 0. Both real and imaginary parts have to be equal to 0 separately. So this implies that d by dx of Rx d phi by dx plus qx phi plus alpha rho x phi minus beta rho x psi. So there is a psi as well, and d by dx of Rx psi by x plus qx psi plus alpha rho x psi and plus beta rho x, it's not minus, plus beta rho x, sorry, this is minus, this is plus, and plus beta rho x phi is equal to 0. So these are the two equations. Here you are getting psi and here you are getting phi. In phi equation psi and in psi equation phi. So these are coupled equations. So I got these two equations. Now, and boundary condition as well, we will use them later. Let's call this 1, let's call this 2. Again, I can multiply 1 by psi and this by phi and subtract. Multiplying 1 by psi and 2 by phi and subtracting. So if I do that, I'll get first equation is multiplied by psi. So psi d by dx of R d phi by dx minus phi d by dx of R d psi by dx. This is from the first two, this is what you will get. Qx phi psi and qx psi phi, they will be cancelled. Alpha rho x phi psi and alpha rho x psi phi, they will be cancelled. Here I will get minus and minus, this will not be cancelled. So it's beta rho phi psi minus beta rho phi psi will give you minus 2 beta rho phi psi minus beta rho x rho, and of course here multiplied by psi, so it is psi square and it is phi square. So minus beta phi square plus psi square, this will be common, is equal to 0. Equal to 0. Alright, so this is what you got. So again I can keep this on the left and bring this on the right hand side. So this whole thing will be equal to, if I send this to the right hand side, they will be on the right hand side, but the left hand side I can, so again as we did in the previous proposition, I can write this as d by dx of psi x or x phi prime of x minus phi x or x psi prime of x equal to, I can bring this beta to the right hand side, and this is phi square x plus psi square x. Alright, this is what you got. Here again, if you simplify it, the derivative, you can impose the product rule on these two functions, like product on these two gives you 4 terms. Psi as it is, the derivative of this, which is the first one, plus the derivative of psi and this as it is, psi prime or phi prime. Here phi prime or psi prime, they will cancel, and plus you will get phi x as it is the derivative of this thing. So again 2 terms will be cancelled, you will get 4 terms, but 2 terms will be cancelled and you will be left with these 2 terms. So it's very easy to verify this one. And now if you integrate, of course d is up front, you can integrate, right? So integrating from a to b, we obtain, I'm writing this on the left hand side, so you can write beta constant a to b rho x phi square x plus psi square x plus psi square x dx equal to, we are done with the integration. So you got rx times, rx is common, you see this integration is gone, so rx is common, psi x phi prime minus phi x psi prime, psi x phi prime minus phi x psi prime, and it is from a to b because we have integrated this. So r at b psi b phi prime b minus phi b psi prime b, and then we have a, so minus r at a, and this whole thing is at a. This is what you get. Now again by using the boundary conditions, we can convert these to r of b. So psi prime of b can be written as, phi prime of b can be written as minus alpha 2 by beta 2 phi at b, right, phi prime of b, and similarly psi prime b can be written as minus alpha 2 by beta 2 psi at b, right, from the boundary condition. As before in proposition 1 we used them, so they are exactly the same equation. So again psi of a, nothing different, it is minus alpha, now at a it is alpha 1 by beta 1 phi of a, and minus phi of b, so phi of a, and psi is again minus alpha 1 by beta 1 psi at a. So again you see now they are cancelled, plus alpha 2 by beta 2 phi b psi b, so it's minus alpha by 2 beta 2 psi b phi b, so you got rb 0 minus ra 0. So it's again the very same thing which we have done in the last proposition, so this come out to be 0. So I got from a to b rho x phi square x plus psi square x dx, this is equal to 0. Alright, now according to the given condition that rho x preserves the same sign in AB, it means row of x will never be equal to 0 for any x in AB. For any x, because you see, if your function preserve only negative sign or positive sign, all right, it means it will never be 0, because to cross this x-axis you have to change your sign. All right, so this implies that row of x is not equal to 0, and ux is the eigen function. This implies that ux is also not equal to 0. So this implies that phi x and psi x cannot be 0 simultaneously. One of them may be equal to 0, all right, but they will simultaneously will not be equal to 0. So this implies that, so as this cannot be simultaneously equal to 0, it means phi square x plus sin square x will not be equal to 0 as well, identically, because one of them may be equal to 0 but other will be non-zero, so square of that will be non-zero. So row of x is not equal to 0, phi square plus sin square is not equal to 0. It means that row x times phi square x plus psi square x dx from A to B is not 0. All right, but we see that the product with beta, product of this whole thing with beta is equal to 0. This implies that beta is equal to 0, because one of them has to be equal to 0 in the product, right? One of them in this product has to be equal to 0. So we proved that this integral thing cannot be equal to 0, so beta has to be equal to 0. If beta is equal to 0, then lambda is equal to alpha plus iota. 0 is your eigenvalue, which is alpha, a real number. All right, so it means that what we have assumed at the beginning, that lambda can be complex, and we can take lambda is equal to alpha plus iota beta. So what we have proved at the end, that even if you take lambda to be complex, beta will come out to be equal to 0, and you will be left with only alpha, which is a real number. So eigenvalues have to be real in this case. All right, so this implies that eigenvalue are real. All right, because the complex part has vanished, the imaginary part has vanished, and this is what we needed to prove. All right, so the things which I skipped were very easy. You see, I replaced this phi x by this thing, and phi psi x, phi b, psi b. So these are very same as in the proposition 1. Like if you want explanation on that, it is the same as proposition 1. I did nothing. Alpha 1 phi of A plus alpha 2 u of A plus beta 1 u prime of A was 0. Let's say this is one of the conditions I'm using. So this implies that alpha 1 u of A is phi A plus iota phi A, psi A. All right. Similarly, plus beta 1 u prime is phi prime of A plus iota psi prime of A is equal to 0. Again, if I combine real and imaginary parts, I will get alpha phi 1 plus beta 1 phi prime of A is equal to 0. And from here, your phi prime of A is equal to minus alpha 1 by beta 1 phi of A. From imaginary part, you have phi prime of A alpha 1, you are getting psi of A, and plus beta 1 psi prime of A is equal to 0. And from here, psi prime of A is equal to minus alpha 1 by beta 1 psi of A. So this is what we used. If you see here, what we used is, we used phi prime of A is equal to minus alpha 1 by beta 1 phi of A, and psi prime of A is equal to minus alpha 1 by beta 1 sin of A. So similarly, if I use the other condition at B, if I use the condition at B, what I will get, phi prime of B is equal to minus alpha 2 by beta 2, because in that case it is alpha 2 and beta 2. All right. So similarly, your phi prime at B will be minus alpha 2 by beta 2 phi at B, and psi prime at B will be equal to minus alpha 2 by beta 2 phi at B. So these are the four relations which we used in this calculation, and it came out to be 0 for both the expressions. All right, and that's how we got 0 on the right hand side. So that was little explanation of my calculation on the left. So we have proved these two propositions. One is your eigenfunctions corresponding to the distinct eigenvalues of the regular Sturm-Liouville problem are orthogonal with respect to the weight function rho of x. And the second proposition that we proved is if rho x preserves the same sign, whether it's positive or negative doesn't matter, then your eigenvalues of the regular SL problem must be real eigenvalues. All right, so these two were the propositions. So what we did today is we studied SL problem, what is the SL equation, and what is the Sturm-Liouville system, and then we discussed the three classification, that when it will be regular SL problem, when it will be singular, and when it will be periodic SL problem. And then we went on to study the properties of the regular SL problems, because regular SL problems are the most important among all SL problems. And if you have seen in the separation of variables, every time we get this regular SL problem with special or x, qx, and px. All right, so we can solve those SL problem, find the eigenvalues, eigenfunctions, and because we have a general theory that whenever eigenvalues are distinct, your eigenfunctions will be orthogonal. So we don't need to prove them again and again. All right, so we have been using this theory in the past lectures, but now we are constructing the rigorous theory of SL problem. So in these lectures. So what we did in the previous lecture was the special case of the SL problem. In this lecture, we studied the general case of the SL problem. But in general case, we had three types of SL problems, and we studied the properties of only the regular SL eigenvalue problems. So this is it for today's lecture. Thank you very much for being with me. I'll see you in the next lecture. Till then, Allah Hafiz. Assalamu alaikum.